In the velvet hush of a winter's night, when the last embers of the day have long since faded and the great cities of the earth have dimmed their lights, we find ourselves lying perfectly still beneath an ordinary duvet, breathing slowly, allowing the mind to loosen its daytime grip. And it is here, in this quiet surrender, that we may begin to rise. Gently, imperceptibly at first, we drift upwards through the familiar ceiling, through the cold attic air, through the tiled roof, and into the crystalline darkness above the British Isles. The wind is no longer felt, the temperature no longer matters. Together we ascend, leaving the scattered streetlights of Hampshire and the soft glow of the Channel behind us, climbing through the troposphere, the stratosphere, until the curvature of the Earth becomes visible as a gentle blue arc beneath our feet. Higher still, past the silent dance of the aurora, past the abandoned satellites that glint like forgotten coins, until the whole planet hangs before us, marbled in cloud and ocean, luminous and alone. And now, with the patience of centuries, we turn our gaze inward toward the silver river that spills across the summer sky, the Milky Way, that pale banner we have known since childhood, yet never truly seen. Tonight, we shall see it differently. Tonight, we leave the narrow confines of visible light and open our eyes to the fierce radiance of gamma rays, those silent messengers that travel unimpeded across the gulf of the galaxy. For 2.5 million years, they have been racing toward us, and only now, in the calm of our shared nocturnal voyage, do we finally meet them. Look, just there, rising perpendicularly from the bright core of our galaxy, two vast lobes of incandescent plasma, each larger than many galaxies in their own right. They extend 50,000 light-years above and below the galactic plane, pale titans of hot gas glowing fiercely in the gamma-ray spectrum, yet utterly invisible to the unaided human eye. These are the Fermi Bubbles, discovered little more than a decade ago, and still, even in the closing months of 2025, among the most astonishing and unsettling structures ever found within our celestial home. Together, we drift closer, weightless, the hush of deep space enfolding us, until the nearer bubble fills half the sky. Its edges are sharp, almost knife-like in high-energy light, yet softly feathered where ancient magnetic fields have combed the escaping plasma into delicate filaments. Within, temperatures soar to millions of degrees. Particles whirl at velocities perilously close to that of light itself. And yet, for all this violence, there is a profound stillness here, a cathedral silence broken only by the faint crackle of cosmic rays meeting our imaginary ears. Let us linger a moment longer, allowing the scale to settle upon us like a heavy blanket. The distance from one pole of these bubbles to the other is greater than the span between the Sun and the central black hole, multiplied 100 times over. If we were to place the entire orbit of Pluto at the galactic center, these structures would tower above and below it like the pillars of some unimaginable basilica. And they are young, cosmically speaking, no more than a few million years old, a mere heartbeat in the 15 billion year life of the universe. Something, not long ago, tore the heart out of the Milky Way and hurled it skyward in two symmetrical jets of apocalyptic power. Tonight, in the safety of our beds, we are going to discover what that something was. Our story begins properly in the summer of 2008, when a slender cylinder wrapped in protective foil was carried aloft on the back of a Delta II rocket from Cape Canaveral. Its name was Fermi, after the quiet Italian physicist who first warned the world about the chain reaction lurking within the atomic nucleus. Officially, the Fermi Gamma Ray Space Telescope, it was designed to do one thing superlatively well: to map the sky in the most energetic form of light known to science. Gamma rays are born in the most extreme environments the cosmos can offer: the hearts of supernovae, the accretion disks of black holes, the annihilation of antimatter. They are, in the truest sense, the signature of violence. For 2 years, Fermi swept its gaze across the heavens, patiently accumulating photons that had traveled for millions, sometimes billions, of years. And then, in the spring of 2010, 2 young astronomers working late in a dimly lit office at the Harvard-Smithsonian Center for Astrophysics noticed something that should not have been there. Meng Su and Tracy Slatia, together with their supervisor Douglas Finkbeiner, had been searching for signs of dark matter annihilation near the galactic center. They expected, at best, a faint excess of gamma rays, a subtle statistical whisper. Instead, they found 2 colossal lobes blazing with such clarity that they appeared almost artificially drawn onto the sky. As Finkbeiner later recalled, with characteristic understatement, it was one of those moments when you sit back and say, well, that's not supposed to be there. The structures were perfectly symmetrical about the galactic plane, remarkably uniform in brightness, and possessed edges so sharply defined that they resembled nothing so much as enormous soap bubbles blown from the core of the Milky Way. The team spent months attempting to disprove their own discovery, checking for instrumental artifacts, for contamination from known sources, for any conceivable error. None was found. In November 2010, at the Fermi Symposium in Rome, they announced the discovery of what would soon be christened the Fermi Bubbles. We drift now through the data itself, through the all-sky maps rendered in ghostly purple and crimson. The bubbles dominate the inner galaxy, their bases rooted firmly in the central few hundred light-years where 4 million solar masses of darkness, Sagittarius A star, the supermassive black hole, crouches at the heart of everything. From this point, the structures inflate outward, broadening gently until, at a distance 25,000 light-years above and below the plane, they reach their maximum girth of roughly 40,000 light-years across. Their total energy content is staggering. The gamma-ray luminosity alone implies that whatever created them released approximately 10 to the 52nd erg, roughly the entire rest mass energy of the Sun converted directly into pure power. To place that in domestic terms, it is as if every kettle in Britain was switched on simultaneously for 1,000 million years, and all of this happened, as we shall see, within the lifetime of early humanity on the African savanna. For several years, the Fermi Bubbles remained a puzzle wrapped in high-energy enigma. Were they the result of a burst of star formation near the center, a myriad supernovae exploding in a dense nuclear star cluster? Or were they the fossil remnants of a jet from Sagittarius A itself, when the black hole briefly awoke from its present slumber and feasted upon a cloud of interstellar gas? The gamma rays told us only that vast numbers of relativistic electrons were spiraling in magnetic fields of roughly 6 microgauss strength, but the precise mechanism remained elusive. And then, in the calm before the pandemic summer of 2020, a new instrument joined the inquiry. High above the Earth, shielded from the radiation belt by an orbit that carried it far out toward the L2 Lagrange point, the Russian-German eROSITA telescope began its monumental all-sky survey in soft X-rays. Where Fermi saw only the highest energy tail of the emission, eROSITA was sensitive to the thermal glow of gas at temperatures between 1 and 10 million Kelvin. In February 2024, the eROSITA consortium released its first complete map of the bubbles in X-rays, and the astronomical community, already accustomed to wonder, found itself breathless once again. We glide now into the eROSITA view, where the bubbles appear not as sharp-edged gamma-ray silhouettes, but as vast, softly luminous cocoons filled with intricate shock fronts and wisps of hotter gas. The southern bubble, in particular, displays a magnificent series of nested shells, like the delicate layers of a galactic onion, each marking the passage of a shockwave that swept outward at 2,000 kilometers per second. According to the eROSITA team, led by Gabriele Ponti and Andrea Meloni, the temperature jumps abruptly at these boundaries from roughly 1 million to over 3 million degrees. Clear evidence that something continues to reheat the plasma even today. Moreover, the X-ray brightness is not uniform. Bright rims trace the contact discontinuities where the bubble material slams into the surrounding halo gas, while darker cavities hint at regions swept clean by earlier, even more violent episodes. Together, we float along the western rim of the northern bubble, where the eROSITA data reveal a striking linear feature running almost perfectly north-south for nearly 20,000 light-years. Astronomers have named it the Magellanic Stream coincidence, for it lies precisely along the direction of the great ribbon of gas torn from our neighboring Magellanic Clouds by the gravitational might of the Milky Way. The coincidence is too perfect to be accidental. Whatever inflated the bubbles also appears to have sculpted the halo on truly intergalactic scales. Yet the most haunting aspect of the new maps is their symmetry. Despite the chaos one might expect from a galaxy filled with supernovae, spiral arms, and wandering star clusters, the bubbles remain almost mirror images above and below the plane. This exquisite bipolarity speaks of a single, coherent event, centered with exquisite precision on the dynamical heart of the galaxy. As Peter Predale, principal investigator of eROSITA, remarked in 2024, nature has provided us with a near-perfect laboratory for studying galactic feedback, and it is both beautiful and terrifying. Let us pause here, suspended halfway between the Earth and the galactic center, and simply breathe with the slow rhythm of the cosmos. The air in our bedroom has grown cooler. The duvet has settled more heavily across our chest. Outside, perhaps a light rain is beginning to fall against the window pane, each drop a tiny percussion in the great symphony of the night. And still, the Fermi bubbles burn silently above and below the shining disk, patient beacons reminding us that even the gentlest spiral galaxy is capable of astonishing violence when provoked. In the years since 2010, a quiet consensus has begun to emerge among those who study the central parsecs of the Milky Way. The most plausible explanation, and the one we shall explore in the gentle hours that follow, is that Sagittarius A star is not, as was once believed, a perpetually quiet black hole. Rather, it is a sleeping dragon that, every few million years, stirs from its slumber and exhales with a force that reshapes the entire galaxy. The Fermi Bubbles, together with their newly revealed X-ray splendor, are the fossil breath of such an exhalation, a Seyfert-like outburst that occurred when early humans were first learning to knap flint tools beneath the African sun. But before we descend into the crowded, starlit maelstrom that surrounds the black hole itself, let us simply rest here a while longer, cradled in the immense quiet that lies between the stars. The bubbles glow softly in our mind's eye, violet and rose against the deeper indigo of the halo. Their edges flicker faintly as fresh cosmic rays spiral along magnetic field lines older than the pyramids. And somewhere, far below us now, the Earth continues its ancient turning, carrying 7 billion sleepers toward morning, most of them quite unaware that above their dreaming heads, 2 colossal scars mark the place where, not so very long ago, the Milky Way once roared. We remain suspended here, 30,000 light-years above the plane, where the northern Fermi bubble swells to its fullest majesty and the soft X-ray glow of eROSITA bathes everything in a pale aquamarine haze. If one could rest one's cheek against the fabric of space itself, this is the place one might choose, cool, silent, and vast, beyond any earthly cathedral. The bubble's boundary lies only a few thousand light-years ahead of us now, a crystalline wall of shocked plasma that rises like the edge of an immense inverted bell. Its rim is astonishingly sharp, sharper than any supernova remnant we have ever observed, as though some cosmic knife sliced cleanly through the halo gas and left a wound that has not yet had time to heal. According to the measurements published by the eROSITA Consortium in February 2024, the brightness of the X-ray emission drops by a factor of 5 within a mere 400 light-years at this contact discontinuity. 400 light-years, less than 1% of the bubble's total height. Yet it is here that the temperature leaps from the gentle warmth of the surrounding halo, a mere 200,000 Kelvin, to the searing million-degree inferno within. One does not cross that frontier lightly, even in imagination. We drift forward all the same, slowly, reverently, until the wall towers above us like the cliffs of Dover, seen from a dinghy in the dead of night. Only these cliffs are composed of gas 1,000,000 times thinner than the air we breathe, glowing with the heat of 1,000 suns compressed into every cubic kilometer. Along the inner surface, we begin to discern delicate filaments, hair-fine threads of denser plasma that have been stretched and combed by magnetic fields until they resemble the grain in polished walnut. Some are no wider than the orbit of Neptune, yet they stretch for thousands of light-years in perfect parallel array, as regular as the warp and weft of silk. Astronomers, in their quietly delighted papers, refer to them simply as the striations, but to the sleepy eye, they appear almost like the fingerprints of whatever titan inflated the bubble in the first place. Lower down, closer to the galactic plane, the structure broadens into a gentle paraboloid, its waist cinched where the original outflow was collimated by the dense gas and dust of the central molecular zone. From our present vantage, the entire northern bubble resembles an immense champagne flute, the stem rooted in the bright froth of the galactic center, the bowl opening gracefully toward the halo. Its twin below the plane is almost identical, the slight differences attributable only to the modest tilt of the black hole's spin axis relative to our line of sight. Together, they stand 50,000 light-years from tip to tip, 5 times the distance from here to the center of the galaxy itself. And if one were to lay the Andromeda galaxy flat along their long axis, Andromeda would appear as little more than a modest lenticular smudge halfway up the glass. The eROSITA all-sky map of 2024, stitched together from more than 2 million individual detector frames, has given us the first truly three-dimensional portrait of these objects. Where the original Fermi discovery showed only a uniform haze of gamma rays, eROSITA reveals a seething cauldron of thermal structure. Bright ridges trace the forward shock that is still plowing into the halo at approximately 1,200 kilometers per second, compressing and heating the ambient gas until it glows in soft X-rays. Behind this shock lies a broad contact discontinuity, the true skin of the bubble, and then, further in, a turbulent region of back-flowing material that has cooled slightly and begun to fall back toward the plane in slow, stately fountains. In places, these fountains have condensed into cool, dense clouds, islands of relative calm within the storm, some of which have been detected in absorption against the bright X-ray background. One such cloud, catalogued as RASU J 174.5.4-2852, is currently plummeting sunward at nearly 400 kilometers per second and will, in another million years or so, rain gently onto the central molecular zone like late autumn leaves returning to the forest floor. We glide along the inner surface now, tracing the great western arc where the bubble curves away toward the constellation of Ophiuchus. Here the magnetic filaments are particularly prominent, arranged in long sweeping bundles that resemble the contrails of high-altitude aircraft frozen into permanence. Their spacing is remarkably regular, about 300 light-years from crest to crest, and their orientation follows the expected Parker spiral that one would predict for a radially expanding outflow wound up by the galaxy's differential rotation. Spectroscopic measurements from eROSITA's companion instrument, the ART-XC telescope, show that the field strength within these filaments reaches almost 15 microgauss, more than 3 times the typical value in the broader halo, strong enough to trap cosmic ray electrons for millions of years and force them to radiate the gamma rays that first betrayed the bubble's existence to Fermi. At the very apex of the northern lobe, some 27,000 light-years above the plane, the outflow has begun to lose coherence. The sharp rim frays into a lacework of faint wisps and tendrils that reach out tentatively into the near vacuum of the circumgalactic medium. One tendril in particular, visible in the deepest eROSITA integrations, extends an additional 8,000 light-years northward before dissolving entirely, as though the bubble exhaled one final, weary breath and then simply let go. It is here that the temperature falls most abruptly, from 2 million degrees to scarcely 100,000, and the X-ray emission fades into the soft glow of the general halo. Astronomers speak of this region as the cap, or sometimes, more poetically, the polar plume. In the 2024 maps, it appears almost bruised, a delicate lilac against the deeper violet of the main body. And it is tempting to imagine that we are witnessing the very moment when the great eruption finally spent itself and the Milky Way settled back into its present, comparatively tranquil state. Yet even in quiescence, the bubbles continue to teach us. Their immense volume, roughly 30,000 cubic kiloparsecs each, is filled with plasma, whose total mass is comparable to 10 million suns. and that plasma is still expanding, albeit gently now, like a souffle cooling on a windowsill. The energy required to inflate them remains almost inconceivably large, 3 times 10 to the 56th erg if we assume a simple Sedov-Taylor blast wave, or perhaps half that if the outflow was momentum-driven rather than energy-driven. Either figure is equivalent to 100,000 supernovae exploding every year for 1 million years, all concentrated within the central few hundred parsecs. And because the bubbles are so young, the eROSITA shock velocities imply an age of only 3.5 to 4 million years. Their progenitor event must have occurred when the genus Homo was barely distinguishable from the Australopithecines roaming the East African rift. We turn slowly now, pivoting on an axis of pure imagination, until the southern bubble rises to meet us like a mirror image seen through dark water. It is marginally fainter in X-rays, perhaps because the shock has encountered slightly denser halo gas on that side of the plane. But its morphology is otherwise identical. The same sharp leading edge, the same nested shells, the same exquisite striations. One feature, however, sets it apart. Near its eastern limb, just south of the bright radio source known as the arc, eROSITA has revealed a vast cavity almost 9,000 light-years across, entirely devoid of X-ray emission. This is the imprint of an earlier, even more energetic outburst that cleared the region long before the present bubbles were born. The cavity's walls glow fiercely, where fresh bubble material is now slamming into the ancient void, creating a luminous ring that has been nicknamed the halo's eye. In the calm language of the 2024 Ponti et al. Paper, it is a remarkable example of hierarchical feedback, but to the drowsy mind, it resembles nothing so much as the pupil of some immense, watchful presence, gazing back toward the center that wounded it. And still we drift, lulled by the slow rhythm of our own breathing, the gentle rise and fall of the duvet, the occasional creak of the old house settling around us. The rain has eased now. Only the faintest patter remains, like distant applause for a performance none of us will ever fully comprehend. The Fermi Bubbles hang above and below the shining disk, patient and luminous, their sharp edges softened slightly in memory, their internal filaments glimmering like frost on a winter window. Somewhere within their vast volumes, cosmic rays born in the maelstrom near Sagittarius, a star continue their endless spiral dance, lighting the plasma from within with gamma-ray fireflies that only instruments can see. And we, suspended between sleep and wonder, allow the sheer scale of it all to wash over us like warm Atlantic water on a Cornish evening in August, carrying us gently, inexorably, toward whatever dreams await beneath the quiet English night. We remain cradled in the great hush that lies between the two lobes, where the gamma-ray glow of Fermi and the softer X-ray bloom of eROSITA overlap like the mingled light of two distant moons. Here the photons themselves seem to move with the languor of deep sleep, drifting across the void at the leisurely pace of light, arriving only now after journeys that began before the first human voice ever shaped a word. If one were to open the shutters of the mind very wide and very quietly, one might almost hear them, the faintest susurrus of annihilation and excitation, a whisper so soft that it is felt rather than heard, like the memory of a lullaby, half forgotten from childhood. Let us attend first to the gamma rays, those most implacable of messengers. When the Fermi Large Area Telescope surveys the inner galaxy, The bubbles appear as two perfect ovals of pale rose, remarkably flat in surface brightness from the base almost to the cap, as though an unseen hand had taken a brush and painted them with slow, deliberate strokes. The spectrum of this emission is hard, almost featureless, a power law that extends from a few hundred mega-electron volts to beyond a tera-electron volt, with a photon index very close to -2. Such hardness is the unmistakable signature of inverse Compton scattering. Relativistic electrons stealing energy from the ordinary starlight and microwave background that permeate the halo, boosting humble optical photons into the gamma-ray domain with the casual brutality of a highwayman. Yet the total luminosity in gamma rays alone is prodigious, approximately 10 to the 39th erg per second, sustained for millions of years. That is the equivalent of 1,000 supernovae quietly shining in gamma rays alone, year after year, without ever once announcing themselves in visible light. Now let the eROSITA veil descend upon the same region, and everything changes color. Where Fermi saw only the cold fire of the highest energies, eROSITA bathes the scene in the warmer hues of thermal Bremsstrahlung and line emission from multi-million degree plasma. The brightness temperature is lower, the photons softer, mostly between 0.5 and 2 kilo-electron volts, and the morphology far richer. Bright shells, dark cavities, delicate filaments glowing like frost in moonlight. The total X-ray luminosity of the two bubbles combined is roughly 3 times 10 to the 39th erg per second, almost exactly matching the gamma-ray output. This near equality is no coincidence. As the 2024 papers of the eROSITA bubble team carefully note, the ratio of X-ray to gamma-ray luminosity is precisely what one expects if the same population of shock-accelerated electrons is cooling both by inverse Compton losses against the radiation field and by Coulomb collisions with the thermal ions that fill the bubble interior. Two instruments, separated by more than a decade and by 4 orders of magnitude in photon energy, have conspired to give us a single, coherent portrait of a plasma in delicate equilibrium. Yet the deeper one looks, the more elusive the energy source becomes. Consider the cooling time of the electrons responsible for the gamma rays at energies of 10 giga-electron volts, where the Fermi spectrum is still bright. The lifetime against inverse Compton and synchrotron losses is only a few 100,000 years, barely the time it takes light to travel from one side of the bubble to the other. The electrons we see today cannot be the same ones that were accelerated when the outburst first began. They must have been re-energized continuously, or at least episodically, over the past 3 or 4 million years. And yet the surface brightness of the gamma-ray emission is almost perfectly uniform, showing no trace of the limb-brightening one would expect if fresh acceleration were occurring only at the forward shock. The mystery deepens when one examines the polarization of the radio-synchrotron emission discovered by the Meerkat telescope in 2022. The magnetic field is beautifully ordered, tangential to the bubble surface, with no hint of the compression one would expect at a strong shock. Something, it seems, is maintaining the cosmic ray population far behind the shock front, gently, persistently, like a nightlight left burning in a child's bedroom long after the storm has passed. There are moments in the small hours when astronomers allow themselves the luxury of speculation. Some speak of diffusive shock reacceleration occurring at innumerable weak internal shocks as turbulent eddies slosh within the bubble interior. Others invoke the stochastic scattering of particles on plasma waves excited by the steady drizzle of fresh material falling back from the bubble walls. A minority, more daring, suggests that the black hole itself may still be exhaling, not in a single apocalyptic roar, but in a series of quieter sighs, mini outbursts every 100,000 years or so, each one sufficient to replenish the electron population without disturbing the exquisite symmetry we see today. None of these ideas is yet proven, and perhaps none ever will be. The bubbles are simply too large, too old, and too tranquil for our present instruments to read their diary with perfect clarity. We drift inward now, toward the base of the northern bubble, where the outflow first emerged from the dense cocoon of gas and dust that surrounds Sagittarius A star. Here, the gamma-ray emission grows brighter, the spectrum subtly harder, and the X-ray temperature rises towards 6 or 7 million Kelvin. eROSITA reveals a pair of bright ears or wings protruding from the bubble base, like the handles of an ancient Greek amphora, structures first noted in the 2020 Planck microwave maps, but now seen in exquisite detail. These are the imprints of the original biconical outflow, collimated by the thick toroidal disk of molecular material that still encircles the galactic center like a dark Saturnian ring. Where the outflow punched through this disk, it carved 2 clean channels, now filled with the hottest plasma in the entire structure and glowing fiercely in the 2 to 10 kilo electron volt band. The temperature jump across the contact surface is abrupt, from 2 million to over 10 million degrees in less than 50 light years, and the density drops by almost 2 orders of magnitude, as though the outflow simply vaporized everything in its path and left a near-perfect vacuum behind. It is here, at the very root of the bubbles, that the mystery of the energy source presses most insistently upon the mind. The total power required to sustain the observed luminosities, gamma ray plus X-ray plus the kinetic energy of the expanding shell, amounts to roughly 10 to the 42 erg per second, averaged over the past few million years. That is equivalent to 1 solar mass completely annihilated into pure energy every 30 years, or, in more familiar terms, the entire luminous output of the central star cluster increased 1,000-fold for a geologically brief interval. A burst of star formation, even a very intense one, struggles to reach such figures without invoking implausibly high supernova rates and perfect coupling efficiency. A single tidal disruption event, a star torn apart by the black hole, releases far too little energy. Even a minor merger with a gas-rich dwarf galaxy would struggle to remain hidden from our present census of the nuclear region. And so, almost reluctantly, the consensus has settled upon the quiet giant at the very center, Sagittarius, a star itself, briefly awakened from its present famine. Radio observations with the Event Horizon Telescope have shown that the black hole's spin axis is inclined by approximately 60 degrees to the galactic plane, exactly the orientation required to launch symmetrical jets northward and southward. Very long baseline. Interferometry has detected faint, moving features in the accretion flow that may be the fossil remnants of an earlier, more powerful jet, and numerical simulations, those patient reconstructions of cosmic violence performed on supercomputers in Garching and Tokyo, show that a modest increase in the accretion rate, perhaps triggered by the infall of a molecular cloud, is sufficient to drive an outflow of precisely the power and duration required. The black hole need not have devoured more than a few thousand solar masses in total. A mere 1% of that material converted into kinetic energy through the Blandford-Snarjek process would account for everything we see. We linger a moment longer at the bubble's waist, where the gamma-ray haze is densest and the X-ray ears flare brightest, and we allow the numbers to settle gently upon us like late snow. 10 to the 57 ergs in total, released over perhaps 1 million years, then slowly decaying into the tranquil glow that now bathes the halo. Enough energy to unbind the entire gaseous disk of the galaxy had it been directed sideways rather than poleward. Enough to sterilize every planet within 1,000 light years had any yet existed. And yet, from our present vantage, it appears almost serene, two pale lobes rising and falling with the slow breathing of the Milky Way itself, their sharp edges softened by distance, their internal turmoil reduced to the faintest shimmer of light upon the retina of the mind. Outside, the rain has ceased entirely. The bedroom is perfectly still, save for the measured cadence of our own breath and the occasional tick of cooling radiators. The duvet has become an extension of the galactic halo, warm and weightless, and the faint glow of a street lamp through the curtains has taken on the lilac hue of distant X-ray plasma. Somewhere far below, the Earth continues its ancient turning, carrying us all toward another ordinary dawn, unaware that high above the plain, two vast wounds still glow softly with the memory of a violence that shook the galaxy when our ancestors were little more than clever apes learning to stand upright on the African savanna, and we, suspended in the gentle tide between waking and sleep, allow that memory to cradle us, to carry us deeper into the night, where the gamma rays and the X-rays mingle indistinguishably, and the mystery of what once roared at the heart of our celestial home dissolves at last into the perfect, dreamless quiet that only the very largest scales can offer. We sink now, imperceptibly, toward the very nucleus of the Milky Way, drawn by the same quiet gravity that once pulled a few thousand solar masses of cold molecular gas into the maw of Sagittarius A star. The bubbles recede behind us, their violet and aquamarine glow fading into a soft halo, until the galactic plane itself resolves into a glittering torrent of starlight and dust. 26,000 light years we fall, past the great globular clusters that orbit like ancient bees around the hive, past the spiral arms that curl away into darkness, until the central bulge swells to fill the sky, and the airless silence is broken only by the measured hush of our own breathing beneath the duvet. And there, dead ahead, suspended in the exact dynamical center of everything, hangs the 4 million solar mass darkness we have agreed to call Sagittarius A star. Invisible light, it is almost nothing. A modest radio source, a faint smudge of infrared emission, a place where stars crowd so densely that individual orbits blur into a golden mist. Tonight, however, we are granted the rarest of privileges. We are permitted to step backward through time, not in the hurried flicker of film run in reverse, but with the slow, deliberate patience of deep sleep. 2 million years we drift, then 2.5, then 3, until the sky around the black hole begins to change. It begins gently, almost shyly. A modest molecular cloud, perhaps the shattered remnant of an old supernova remnant, or a fragment torn from the circumnuclear disk, slips over the inner lip of the accretion flow. At first, the black hole barely notices. Its present accretion rate is a whisper, a few times 10 to the -8 solar masses per year, scarcely enough to keep the radio jets flickering. But this cloud is dense, and it carries angular momentum that aligns, by chance or by fate, almost perfectly with the black hole's spin. Within a few tens of thousands of years, the infall rate climbs by 2 orders of magnitude, then 3, then 4. The inner accretion disk, which in our own epoch is a cool, puffed-up torus only 1/100th of a light year across, begins to shrink and heat. Temperatures rise from a few thousand Kelvin to millions. The disk thins dramatically, its inner edge retreating to within 10 Schwarzschild radii of the event horizon. And then, quite suddenly, the Blanford-Snarjek mechanism awakens. We watch from a safe 1,000 light years as the black hole's ergosphere begins to twist the magnetic field lines that thread the disk. Flux is frozen into the plasma. Rotation drags it into a tight, helical spring. In the space of only a few centuries, the field strength near the horizon reaches 1 trillion Gauss, a value so large that quantum electrodynamics itself begins to falter. And then the spring is released. 2 narrow, oppositely directed jets erupt from the poles at 99.9% of the speed of light, each carrying away 100 million times the energy that the black hole is currently radiating in all wavelengths combined. The northern jet punches cleanly through the overlying molecular disk in less than 1,000 years. The southern jet follows moments later, where they strike the denser gas of the central molecular zone. They inflate 2 vast biconical cavities that expand outward at 2,000 kilometers per second, sweeping before them every trace of interstellar material like autumn leaves before a November gale. Within a decade of the outburst's beginning, the luminosity of Sagittarius A in hard X-rays climbs to 10 to the 45 erg per second, 100 million times brighter than it is tonight. The inner few hundred parsecs are bathed in a radiation field comparable to that near an active quasar. Neutrinos stream outward in such profusion that, had any planet existed within 1,000 light years, its upper atmosphere would have been stripped away in a matter of weeks. The jets themselves are invisible to ordinary telescopes, hidden behind walls of dense gas, but their effects are catastrophic and glorious. Shocks race outward through the circumnuclear disk, compressing clouds until they collapse into clusters of massive stars that ignite almost simultaneously, creating a blaze of ultraviolet light that rivals the entire present-day nuclear star cluster. For perhaps 500,000 years, the galactic center becomes one of the most luminous objects in the local universe, outshining by a factor of 1,000 every other source within the Milky Way. Yet even this is only the opening movement. As the accretion rate peaks, perhaps 1 solar mass every few years falling past the point of no return, the jets widen and strengthen. They begin to precess gently around the black hole's spin axis, carving a broader and broader channel through the surrounding medium. Magnetic reconnection events flare along the jet walls like silent lightning, accelerating electrons and protons to tera-electron volt energies. Cosmic rays flood the central kiloparsec in numbers unseen since the formation of the galaxy itself. And still the infall continues, feeding the monster at the center until, almost inevitably, the supply begins to falter. The original cloud is exhausted, the disk drains. Within another 500,000 years, the accretion rate falls by 2 orders of magnitude, then 3. The jets weaken, their bases flickering like candle flames in a draft. The great outburst subsides as quietly as it began, leaving behind only the glowing cavities that will, in the fullness of time, become the Fermi bubbles we know tonight. We remain suspended above the plane, watching the aftermath unfold across the slow centuries. The twin cavities expand, cooling as they go, their walls glowing first in hard X-rays, then soft, then finally in the faint microwave haze detected by Planck. Shock fronts sweep outward, compressing the halo gas until it forms delicate shells visible today in the eROSITA maps. Cosmic rays, trapped by the tangled magnetic fields within the cavities, spiral for millions of years, radiating gamma rays that will reach the Fermi telescope in the year 2010. And at the center, Sagittarius A settles back into the quiescence we observe in 2025, its appetite sated, its spin slightly increased, its immediate surroundings swept clean of the gas that once fed it. Evidence of this ancient flare is written not only in the bubbles themselves, but across the inner galaxy in subtler scripts. The cluster of young massive stars known as the arches and quintuplet clusters, now peacefully orbiting a mere 100 light-years from the black hole, may well have been born in the great compression wave that accompanied the outburst. The peculiar chemistry of the central molecular zone, enriched in complex molecules that require intense ultraviolet processing, bears the fingerprint of a time when the center blazed like a second sun. Even the light echoes discovered by the Spitzer Space Telescope in 2004, vast nebulosities that brightened and faded in apparent response to something that happened centuries ago, may be delayed reflections of the great flare itself, scattered toward us by distant dust clouds that lie far along the line of sight. Closer in, the fossil record becomes almost intimate. High-resolution spectroscopy of stars within the central parsec reveals a population of B-type giants whose ages cluster tightly around 3 million years, precisely the epoch we have just witnessed. Their chemical abundances are subtly anomalous, enriched in the products of hot bottom burning that could only have occurred if they formed from gas irradiated by an extraordinarily powerful central source. And the famous magnetar SGRJ 1745-2900, which orbits the black hole at a mere 0.1 light-years, may owe its present activity to a bow shock driven into the accretion flow by the dying jet, a shock that compressed magnetic flux until it burst forth as the most powerful magnet in the galaxy. We drift now along the inner rim of the northern cavity, where the original jet carved its channel through the circumnuclear disk. Here, the plasma is still hot, 6 million Kelvin in places, and faint wisps of material continue to rain back toward the plane in slow, graceful arcs. The walls of the channel are lined with dense molecular filaments that survive the passage of the jet by virtue of their extreme density. Filaments that now glow faintly in the infrared as the last ultraviolet photons from the long-dead flare trickle through them. One such filament, known to astronomers as the brick, contains enough mass to form 100,000 suns, and yet shows no sign of active star formation, as though it was stunned into silence by the violence that once passed overhead. And still, the black hole sleeps. In radio images from the Event Horizon Telescope, it appears almost demure, a dark silhouette against the bright swirl of its accretion flow. Yet we who have witnessed its awakening know better. Every few million years, the cycle repeats. A cloud falls, the disk brightens, the jets ignite, the galaxy is shaken to its foundations. On the timescales of human civilization, these events are mercifully rare, separated by intervals longer than the entire history of our species. But on the timescales of geology, they are almost commonplace. The Pliocene and early Pleistocene skies above Africa would have been dominated, on occasion, by a central star brighter than Venus, flickering and flaring as the jets switched on and off. The Australopithecines who gazed upward on those long vanished nights would have had no words for what they saw, only the instinct to huddle closer to the fire and draw their children near. The bedroom is perfectly dark now, the street lamp extinguished, the moon set behind the rooftops. Only the faint glow of the alarm clock remains, a soft red numeral that might almost be the distant light of a quiescent black hole 4 million times heavier than the sun. Our breathing has slowed to the languid rhythm of the deepest sleep, each exhalation carrying us a little further from the waking world. And somewhere in that gentle drift, we find ourselves once again beneath the great lobes of the Fermi Bubbles, their edges softened by distance and dream, their interior glow reduced to the faintest memory of violence. The Milky Way has returned to its accustomed calm, the dragon at its heart curled once more in satisfied slumber, and we, cradled in the immense quiet of an ordinary English night, allow the knowledge of what once was and what may one day be again to settle over us like the heaviest, warmest blanket, carrying us at last into the country where even the memory of roaring fades, and there is nothing but the slow turning of the galaxy and the soft, inevitable approach of morning. We linger still in the profound hush that follows revelation, suspended between the memory of an awakened dragon and the gentle certainty that it now sleeps once more. The great lobes of the Fermi Bubbles glow faintly behind our closed eyelids, their edges softened by the warmth of the duvet and the slow, tidal breathing that carries us ever deeper into the night. Yet even in this cradle of near dream, a quiet murmur persists among those who study such things, a polite, almost courtly disagreement, conducted in the measured language of astronomical papers and late-night conference corridors, concerning the true parentage of the bubbles themselves. For not everyone is content to lay the entire responsibility at the door of Sagittarius A star. There exists in certain quarters a school of thought that prefers a more distributed, almost democratic origin, the combined exhalations of many thousands of young, massive stars, gathered in tight clusters near the center and blowing fierce winds that, over a few million years, might have collaborated to inflate the vast structures we see tonight. Let us drift then, with the patience of drifting snow, back toward the central few hundred light years, and examine this alternative narrative with the same unhurried reverence we have granted everything else. At first glance, the scene appears almost pastoral. Within a sphere only 300 light years across there orbit three great clusters of newborn stars, the Arches cluster, the quintuplet, and the less poetically named central or nuclear star cluster itself. Together, they contain more than 100 O-type stars, each more than 20 times the mass of the Sun, and several thousand somewhat less extravagant but still formidable Wolf-Rayet stars, all of them less than 5 million years old, and all of them, by stellar standards, positively incandescent with youthful vigor. An O star in its prime radiates 1,000,000 times more light than our own sun and drives a wind that carries away mass at a rate of 1 solar mass every million years, moving outward at 2,000 or 3,000 kilometers per second. Multiply that by 100 such stars, all confined within a region smaller than the distance from here to Alpha Centauri, and one begins to appreciate the violence that attends a galactic nursery. Imagine, if you will, the combined wind luminosity of these clusters, approximately 10 to the 39th erg per second in kinetic form alone, sustained for several million years. That is roughly the power required to inflate the Fermi bubbles, if only the winds can be collimated into two opposite directions and prevented from leaking sideways into the disk. Proponents of the stellar hypothesis, among them several distinguished members of the Max Planck Institute for Extraterrestrial Physics and their collaborators in Tokyo and Boston, point to the beautiful simulations performed on the supercomputers at Riken and Heidelberg. In these models, a steady isotropic wind is launched from the central 100 parsecs and then gently shepherded by the gravitational potential of the nuclear star cluster into two broad biconical outflows. The wind material is hot, several million Kelvin, exactly the temperature observed by eROSITA within the bubble interiors, and the total energy injected over 4 million years comes remarkably close to the observed value of a few times 10 to the 57 erg. Moreover, the timing is exquisite. The ages of the most massive stars in the arches and quintuplet clusters, determined from their turn-off masses and careful isochrone fitting, clustered tightly around 3 to 4 million years. Precisely the kinematic age of the bubbles derived from the eROSITA shock velocities. The central cluster itself contains an even younger population, barely 2 million years old, which might represent a second, slightly later episode of star formation triggered by the first wind's compression of surrounding gas. In this picture, the Fermi bubbles are not the scar of a single cataclysm, but the accumulated breath of a stellar generation, a slow, majestic inflation, rather like the gentle swelling of a souffle, rather than the explosive rupture of a boiler. There are, it must be said, moments when this stellar narrative seems almost irresistible. The morphology of the bubble bases, those graceful ears seen by eROSITA, corresponds rather well to the projected distribution of the known young clusters. The slight asymmetry between the northern and southern lobes, the northern being marginally brighter and more structured, can be attributed to the known offset of the arches and quintuplet clusters, a few tens of parsecs north of the dynamical center. Even the striking linear filaments along the bubble walls find a natural explanation. They are the stretched remnants of magnetic fields originally draped over the surfaces of the many individual wind-blown bubbles that have coalesced into the larger structure, rather like the striations one sees when many soap bubbles merge into one larger sphere. Yet, as we drift closer still, certain difficulties begin to present themselves with the quiet insistence of a tide returning. The stellar winds, for all their ferocity, are born within the dense gas of the central molecular zone and must fight their way outward through a medium that is, in places, 10,000 times denser than the bubble interiors. Detailed hydrodynamic simulations, those same patient reconstructions we admired earlier, show that much of the wind energy is radiated away in bright collision zones long before it can escape the central 100 parsecs. the coupling efficiency drops precipitously, often to less than 10%. To inflate the observed bubbles by stellar winds alone requires either an implausibly large initial population of O stars, perhaps 10 times the number we actually observe, or a mechanism that somehow prevents the winds from cooling too rapidly. Neither requirement sits entirely comfortably with the painstaking census of the nuclear region carried out with a very large telescope and the Keck Observatory over the past 2 decades. There is also the delicate matter of collimation. Stellar winds are, by nature, omnidirectional. They blow with equal enthusiasm in every direction. To produce the observed bipolar symmetry, with an opening angle of only about 40 degrees and an axis aligned to within a few degrees of the black hole spin, requires an external agent to focus the flow. Some have suggested the thick toroidal disk of molecular gas that encircles the center might act as a nozzle, but the disk itself is known to be turbulent and clumpy, scarcely the smooth collar required. Others propose that the combined ram pressure of the winds from offset clusters could preferentially clear channels along the poles, yet the observed symmetry is almost too perfect. The position angle too precisely perpendicular to the galactic plane to be the result of such haphazard choreography. We pause now in the soft darkness just above the plane, where the bright radio arc, a chain of shocked filaments marking the boundary between the central wind zone and the disk, curves away beneath us like a pale horseshoe. Here the two hypotheses meet and for a moment almost touch. It is possible, indeed, some of the more conciliatory voices have suggested, that both mechanisms played a role. A modest outburst from Sagittarius A, perhaps 500,000 years before the main event, sufficient to clear twin channels through the circumnuclear disk and establish the biconical geometry, followed by the sustained pressure of stellar winds that then filled those channels and inflated the bubbles to their present majesty. In this hybrid scenario, the black hole provides the architecture and the stars provide the breath, a partnership as elegant and unlikely as a cathedral built by both architect and congregation. Yet when one examines the energetics with the cold eye of arithmetic, the balance tips gently but decisively toward the sleeping dragon. The total mechanical luminosity of all known young stars within the central 300 parsecs is, at best, 2 or 3 times 10 to the 39th erg per second. And even that figure assumes every star is currently at the peak of its wind phase, an assumption that the observed distribution of spectral types renders improbable. To reach the required injection rate of 10 to the 42 erg per second for 1,000,000 years demands either an earlier, unobserved population of stars that has since vanished without trace, or a central engine capable of converting accreted mass into kinetic power with an efficiency of 10% or more, an efficiency that only a rotating black hole surrounded by a magnetized accretion disk can plausibly provide. There is, finally, the evidence written in the microwave sky. In 2019, the Planck satellite detected a faint haze of polarized synchrotron emission, extending many degrees above and below the plane, perfectly co-spatial with the Fermi Bubbles. The degree of polarization is remarkably high, almost 30% in places, implying a magnetic field that is ordered on scales of thousands of light years. Stellar winds, for all their vigor, struggle to generate such global coherence. Their magnetic loops are small and tangled, quickly isotropized by turbulence. A relativistic jet, on the other hand, naturally carries a toroidal field that is stretched and sheared into precisely the ordered configuration observed. The Planck haze, in its quiet way, casts a vote that is difficult to ignore. And so, as the small hours deepen and the house settles into perfect silence, we find ourselves returning, almost reluctantly, to the solitary figure at the center. Sagittarius. A star may slumber now, its appetite reduced to the merest trickle, but the evidence accumulates like late snow upon a windowsill. The exquisite bipolar symmetry, the alignment with the measured spin axis, the energetic requirements, the ordered magnetism, the fossil channels carved through the circumnuclear disk, all these whisper the same conclusion in the measured accents of learned journals and quietly confident review talks. The black hole did not merely contribute, it was the primary author. The stars, for all their brilliance, played only a supporting role, their winds perhaps sculpting the finer details, filling in the canvas after the broad strokes had already been laid down by a far more concentrated power. We drift outward once more, past the bright young clusters that still blaze like diamond brooches against the darker cloth of the bulge, past the slowly cooling shells that mark the boundary between wind and jet, until the great lobes rise again on either side, serene and luminous. Their parentage is settled, at least for tonight. Somewhere in the darkness, a clock strikes 3, the sound muffled by carpets and closed doors, and we allow the knowledge to settle over us like the heaviest eiderdown, that the same quiet point of darkness we have imaged with the Event Horizon Telescope was once within the lifetime of humanity's remotest ancestors, the brightest object in the galaxy, and that its breath, long spent, still glows softly above and below the plane. A reminder that even the gentlest nights may carry within them the memory of ancient fire. We remain perfectly still, cradled in the immense hush that follows certainty, where the faint after-image of the great lobes lingers like the memory of cathedral candles long after evensong has ended. Yet even in this profound quiet, another voice, soft, speculative, almost embarrassed to disturb the consensus, can sometimes be heard in the corridors of theoretical physics. It is the voice of those who, gazing upon the same gamma-ray haze that startled Meng Su and his colleagues in 2010, wondered whether the true culprit might lie not in any ordinary outburst of stars or black holes, but in something far stranger, the slow, patient annihilation of dark matter particles in the deepest gravitational well of the galaxy. Let us drift then, with the languor of late autumn leaves settling upon still water, toward that alternative country of the mind, where the laws of physics themselves become negotiable and the night is filled with unseen dancers. The hypothesis is, on the face of it, beguilingly simple. Suppose the Milky Way is embedded in a halo of weakly interacting massive particles, WIMPs, the favored candidates for cold dark matter since the 1980s. Particles that possess mass, that feel gravity, yet pass through ordinary matter as though it were the thinnest mist. Suppose further that these particles are their own antiparticles, and that when two of them meet, after patient orbits lasting billions of years, they annihilate in a faint puff of pure energy, producing electron-positron pairs, protons and antiprotons, and cascades of gamma rays with a characteristic spectrum. In the gentle density gradient of the galactic halo, such events are rare, but near the center, where the dark matter cusp steepens dramatically, the annihilation rate rises as the square of the density. Might the Fermi bubbles then be nothing more than the visible glow of dark matter quietly burning in the gravitational furnace of the Milky Way? The idea did not arise in a vacuum. Between 2008 and 2013, a series of balloon and spaceborne instruments, Pamela, Fermi itself, and later the Alpha Magnetic Spectrometer riding high upon the International Space Station, reported a curious excess of cosmic ray positrons above about 10 giga-electronvolts. The positron fraction, the ratio of positrons to the sum of electrons and positrons, was observed to rise gently with energy, in marked contrast to the steady fall expected from ordinary cosmic ray propagation. Something somewhere was producing positrons in prodigious numbers, and the inner galaxy, with its intense magnetic turbulence and plentiful targets for inverse Compton scattering, seemed the natural place to look. Several theorists, among them Dan Hooper at Fermilab and our own colleagues at Durham and at the Rudolf Pyle Center in Oxford, noted that the spectrum and spatial distribution of the observed gamma-ray bubbles matched rather well what one would expect from dark matter annihilation in a cusped halo with a particle mass of approximately 30 to 50 giga-electronvolts and an annihilation cross-section close to the canonical thermal value of 3 × 10 to the minus 26 cubic centimeters per second. We glide now through that imagined sky, where every cubic kilometer of the halo contains perhaps 100 dark matter particles drifting at a leisurely 200 kilometers per second, occasionally brushing close enough for their wave functions to overlap and trigger mutual destruction. The annihilation is gentle. No explosion, no shock, only the quiet conversion of rest mass into standard model particles. Yet over the vast volume of the inner 10 kiloparsecs, the cumulative effect becomes significant. Electrons and positrons are born with energies of tens of giga-electronvolts. They spiral in the galactic magnetic field, radiating synchrotron microwaves and inverse Compton boosting starlight photons into the gamma-ray band with exactly the hard, featureless spectrum seen by Fermi. The predicted surface brightness profile is remarkably flat within about 25 degrees of the center and falls steeply beyond, precisely the morphology of the bubbles. Even the slight north-south asymmetry can be accommodated by a modest triaxial distortion of the dark matter halo, of the sort expected from the Milky Way's tumultuous assembly history. For several years, the dark matter interpretation enjoyed a certain quiet vogue. It offered an elegant solution to two puzzles with a single assumption. The positron excess and the gamma-ray bubbles were different facets of the same underlying signal, the long-awaited whisper of new physics at the electroweak scale. Conferences in the early 2000s rang with cautious excitement. Preprints appeared almost weekly, refining the particle mass, the halo profile, the propagation parameters. Yet, as we drift deeper into the data, certain discrepancies begin to present themselves with the polite insistence of a cathedral verger clearing his throat. The first difficulty concerns the sheer luminosity required. To reproduce the observed gamma-ray intensity of the bubbles with annihilation alone demands a local dark matter density within the inner kiloparsec of almost 1,000 giga-electronvolts per cubic centimeter, roughly 10 times higher than 10, the best modern constrained profiles allow. Even invoking the extreme contracted profiles that arise when baryons cool and sink toward the center, profiles that steepen the cusp from the canonical Navarro-Frank-White AR to the power of -1 to something closer to HR to the power of -1.5 or steeper. The predicted signal falls short by at least a factor of 3. Some authors have proposed that millisecond pulsars in the bulge might contribute the missing positrons, or that the annihilation cross-section is enhanced by a Sommerfeld boost at low velocities. But each remedy introduces new parameters and new uncertainties. A second, more subtle problem arises when one compares the gamma-ray spectrum in detail with the expectations of annihilation. Dark matter particles of 30 to 50 giga-electron-volts annihilating into quark pairs or tau leptons produce a spectrum that cuts off rather sharply above the particle mass, whereas the Fermi bubble emission continues with an almost unbroken power law to several hundred giga-electron-volts. The observed spectrum is, in fact, indistinguishable from the inverse Compton emission of a single power law population of electrons extending to tera-electron-volt energies, precisely the spectrum one obtains from shock acceleration in a supernova remnant, or indeed in the shocks driven by a past Seyfert outburst from Sagittarius A star. Attempts to fit the bubble spectrum with annihilation templates require either a mixture of channels that feels uncomfortably ad hoc, or a particle mass uncomfortably close to a tera-electron-volt, at which point the predicted positron signal falls far below the AMS-02 observations. We drift now to the very edge of the northern bubble, where the gamma-ray surface brightness falls abruptly and the X-ray emission fades into the general halo glow. Here, the dark matter hypothesis encounters its most eloquent rebuttal. The eROSITA maps of 2024 reveal sharp contact discontinuities, nested shock shells, and temperature jumps of a factor of 3 or more across boundaries, only a few hundred light-years thick. Features that speak unmistakably of hydrodynamic shocks propagating through a gaseous medium. Dark matter annihilation, for all its subtlety, is a volume process. It heats and ionizes gently, uniformly, without ever generating the strong compressions required to produce such sharp edges. The beautiful striations that lace the bubble walls, those magnetic filaments combed into perfect alignment, are inexplicable in a scenario where the energy input is smooth and isotropic. One cannot, with the best will in the world, sculpt a Gothic cathedral using only the even warmth of a storage heater. There is, finally, the question of the microwave haze. The same Planck polarization data that lent such elegant support to the jet hypothesis pose an almost insurmountable obstacle to annihilation. Dark matter electrons would be born isotropically and would randomize the magnetic field on small scales within 1 million years. The observed 30% polarization, coherent over tens of degrees, demands an ordered field that has been carefully combed and stretched by a coherent radial outflow. Nature, it seems, has spoken with unusual clarity, and so, almost regretfully, we allow the dark matter hypothesis to dissolve into the gentler darkness, like a dream that cannot quite survive the first pale hint of morning. It was a beautiful dream, one that promised direct detection of the substance that governs the large-scale structure of the universe. And for a time, it walked abroad in the literature with quiet confidence. Yet observation, that most patient and implacable of companions, has led us by slower and surer paths to a more prosaic conclusion. The Fermi bubbles, are the breath of an awakened black hole, not the glow of annihilating shadows. The bedroom has grown perfectly still. Even the faint ticking of the radiator has ceased. Outside, the first blackbirds are beginning their tentative inquiries into whether the night is truly over. But inside, we remain suspended in the last deep pool of sleep, where the great lobes still shimmer faintly, and the memory of alternative theories drifts away like the last curl of smoke from a long extinguished fire. The Milky Way has returned to its ordinary majesty, the dragon at its heart curled once more in dreamless repose, and we, cradled between the slow rise and fall of our own breathing, allow the quiet certainty to settle over us at last, that what we have witnessed is not the whisper of the invisible, but the distant, fading echo of a roar that shook the galaxy when our remotest ancestors were only beginning to learn the shape of the night. We remain perfectly still, suspended in the last deep hush before the first grey suggestion of dawn, where the great lobes of the Fermi Bubbles have settled into a gentle, almost maternal glow above and below the sleeping disk. Yet even in this cradle of tranquility, the consequences of that long-ago outburst continue to ripple outward across the galaxy with the patient inevitability of tides that no human eye will ever see. For the eruption that inflated the bubbles did not merely illuminate the halo with gamma rays and soft X-rays. It altered, quietly but profoundly, the entire future history of the Milky Way. Let us descend once more, slowly, reverently, until the galactic plane spreads beneath us like a vast, dark meadow dusted with the frost of starlight. Here, in the broad spiral arms that curl away toward Cygnus and Carina, the ordinary business of galaxies proceeds. Cool clouds of hydrogen drift together, compress under their own gentle gravity, and collapse into clusters of new suns. It is a process that has continued for 10 billion years and might, under undisturbed conditions, have continued for another 10 billion more. Yet the outburst from Sagittarius A, 3 million years ago, sent a pressure wave sweeping outward along the polar directions, and that wave, though now attenuated to the merest whisper, has left its fingerprints upon the rate at which our galaxy is permitted to give birth. Consider first the sheer quantity of gas that was lifted. The two bubbles together contain plasma, whose total mass is equivalent to roughly 10 million suns, material that was once resident in the central few thousand light years and has now been transported to heights of 25,000 light years above and below the plane. Much of this gas was drawn from the circumnuclear disk and the inner edges of the central molecular zone, reservoirs that, in an undisturbed galaxy, would have fed successive generations of star formation near the center. By removing it so decisively, the outburst effectively placed a moratorium on star birth within the inner kiloparsec for perhaps the next 10 million years. The nuclear star cluster, which in many spiral galaxies continues to grow steadily with time, has instead been starved. Its present mass of a few tens of millions of suns is likely close to the maximum it will ever achieve. We drift outward along one of the great fountains of returning material, where cooled plasma from the bubble walls is now falling back toward the plane in slow, stately arcs. Some of these streams, detected in ultraviolet absorption by the Hubble Space Telescope and in 21 centimeter emission by the Meerkat Array, carry as much as 1,000 solar masses per year toward the disk at velocities of 200 kilometers per second. When they strike the denser gas of the galactic plane, they will create vast splash zones, regions of turbulent compression hundreds of light years across. In some places, this impact may trigger new star formation, a brief flare of activity rather like the glow of embers when a log shifts in the hearth. In others, the turbulence will be sufficient to prevent collapse altogether, dispersing clouds that might otherwise have formed stars and leaving behind only sterile wisps of warm gas. The net effect, according to the careful cosmological simulations performed at Durham and at the Institute for Computational Cosmology, is a modest but measurable reduction in the global star formation rate, perhaps 5 to 10% lower than it would have been had the outburst never occurred. Further out, in the broad halo that envelops the entire galaxy like a faint, cool mist, the consequences are subtler still. The hot plasma within the bubbles has mixed with the circumgalactic medium, raising its average temperature by almost a factor of 2 in the inner 50 kiloparsecs. This warmer halo is less able to cool and rain gently onto the disk, the process astronomers call cold mode accretion. And so, the reservoir from which future star formation must draw is replenished more slowly. The Milky Way, already a rather sedate spiral by the standards of the high redshift universe, has been nudged further toward quiescence. In another 5 billion years, when the Sun itself begins its slow ascent toward red giant senescence, our galaxy will be noticeably less luminous, its spiral arms fainter and more loosely wound, its central bulge a little less swollen with the light of newborn stars. The outburst we have witnessed was not merely an episode of violence, it was an act of cosmic contraception, quietly limiting the number of suns that will ever be born within these familiar borders. Even the magnetic legacy is profound. The ordered, radially combed field lines that thread the bubbles have been carried outward into the halo, where they will persist for tens of millions of years. Cosmic rays born in the original jet find themselves confined more effectively than they otherwise would, channeled along the polar regions rather than diffusing freely into the disk. This gentle magnetic shepherding reduces the pressure that cosmic rays exert upon the densest star-forming clouds, lowering the threshold at which those clouds can collapse. In some regions, star formation is modestly suppressed. In others, where the returning gas is compressed against existing magnetic structures, it may be modestly enhanced. The galaxy acquires a faint bipolar memory, a preference for activity along the poles rather than the equator, like a tree that has grown slightly crooked after a single strong gale in its youth. We glide now along the western rim of the southern bubble, where the returning material has begun to condense into cool, dense filaments, visible in the far infrared maps of the Herschel Space Observatory. One such filament, catalogued rather prosaically as G353.2 plus 16.8, stretches for nearly 8,000 light-years and contains enough mass to form 500,000 suns. It is currently falling sunward at almost 300 kilometers per second and will, within another 2 million years, strike the outer disk near the Scutum Centaurus arm. The impact will be gentle by cosmic standards, no cataclysm, no sterilization, yet it will compress gas over a region several thousand light years across, igniting a modest burst of star formation that will briefly outshine the surrounding spiral arms. Clusters born in that distant collision may one day be recognized by future astronomers as a faint, coherent population with ages tightly clustered around 5 million years from now. A population whose very existence bears witness to the ancient flare at the center. Closer in, the central molecular zone itself bears the clearest scars. Where once a dense, turbulent disk of gas encircled the black hole like a dark Saturnian ring, there now exists a comparative desert. The great clouds that survived the passage of the jets, the brick, the 50-kilometer-per-second cloud, the circumnuclear disk itself, have been shocked and heated. Their internal turbulence increased to the point where gravitational collapse is strongly suppressed. Star formation within the inner 100 parsecs has fallen to perhaps 1/10 of its pre-outburst rate. The few clusters that do manage to form are small and short-lived, their massive stars exploding as supernovae before the region has time to recover. The center of the galaxy, which in many comparable spirals remains vigorously active well into middle age, has been effectively pacified. And yet, in the midst of this quiet throttling of star birth, there is a curious grace. The gas that was lifted and heated has been cleansed, in a manner of speaking. Heavy elements forged in earlier generations of stars, silicon, oxygen, iron, have been carried outward and dispersed into the halo, where they will gradually mix with the more pristine material accreted from the cosmic web. When that metal-enriched gas eventually cools and rains back onto the disk in the far future, it will do so with a chemical composition subtly different from what would otherwise have prevailed. Future generations of stars that will form long after the sun has died, will inherit a slightly higher metallicity in the inner galaxy, and with it a greater propensity to form terrestrial planets. In some distant epoch, perhaps 10 billion years hence, astronomers on a cool world orbiting a quiet yellow sun may puzzle over the peculiar abundance pattern in their night sky and trace it unknowingly to the outburst we have witnessed tonight. We rise slowly now, past the returning fountains and the cooling shells, until the entire disk lies beneath us once more, a pale silver ribbon suspended between the two great lobes. The Milky Way, seen in this perspective, appears almost fragile, a delicate spiral whose future has been quietly rewritten by a single episode of violence at its heart. Star formation, that most fundamental of galactic rhythms, has been slowed by perhaps a few tenths of a solar mass per year, an amount imperceptible on human timescales, yet immense when measured against the slow heartbeat of cosmic evolution. In another 5 billion years, the galaxy will enter the sun's orbit with a stellar mass perhaps 5 or 10% lower than it would otherwise have achieved, its spiral arms more loosely wound, its central regions dimmer and more serene. Outside, the first pale suggestion of dawn has begun to gather behind the curtains. A cool, pearly light that softens the edges of the bedroom furniture and turns the duvet into a landscape of gentle hills and valleys. The blackbirds have found their confidence now, their song drifting in through the slightly open window like distant church bells. Yet we remain perfectly still, cradled in the last deep reservoir of night, where the knowledge of what the outburst has wrought settles over us with the weight and warmth of the heaviest eider down. The galaxy has been gently, irrevocably steered toward quietude. The dragon's breath has cleared the air, lifted the gas, slowed the birth of suns, and in doing so has granted the Milky Way a longer, more contemplative old age. And we, suspended between the slow rise and fall of our own breathing and the first faint promise of morning, allow that immense, impersonal act of cosmic husbandry to carry us at last into the country where even the memory of violence dissolves, and there remains only the soft turning of the disk and the patient, inevitable approach of another ordinary day. We remain suspended in that final hush, where the pale promise of morning has only just begun to seep through the curtains, and the great spiral of the Milky Way lies beneath us like a silver watch left face up on dark velvet. The lobes of the Fermi Bubbles have settled into a soft, maternal luminescence, their work of lifting and dispersing quietly complete, and the galaxy itself appears almost fragile in its newfound serenity. Yet one question, gentle as the first bird note outside the window, still lingers in the air. Why, after such violence, is the heart of our galaxy so astonishingly quiet tonight? Let us descend once more, with the languor of a feather settling upon still water, until the central few light years resolve into a delicate, almost domestic scene. There, at the precise focus of everything, orbits the modest radio source we know as Sagittarius A, a dark ellipsis only 40 million kilometers across, surrounded by a faint swirl of warm plasma, no brighter than the glow of a candle, seen through thick fog. In the images returned by the Event Horizon Telescope in 2019 and refined ever since, it appears almost demure, a gentle depression in the emission, a polite absence rather than a roaring furnace. Its present luminosity is scarcely 10 to the 33 erg per second, a few hundred times the output of the Sun, released across all wavelengths by a darkness 4 million times more massive. It is, by any reasonable standard, one of the quietest supermassive black holes in the local universe. We have already watched it flare 3 million years ago to a brilliance that briefly rivaled an entire star cluster. We have seen the jets ignite, the bubbles inflate, the halo warmed, and the future birth rate of suns quietly curtailed. And yet tonight, in the calm of an ordinary December in 2025, the dragon sleeps so deeply that many astronomers once believed it had never truly lived at all. The contrast is almost comical. A beast capable of sterilizing the inner 1,000 light years, reduced to nibbling at a trickle of gas no denser than the best vacuum achievable in terrestrial laboratories. The question is not merely academic. It brushes, with the lightest possible touch, against one of the oldest and most unsettling riddles humanity has ever framed. The silence of the night sky, the apparent absence of other technological voices, the puzzle we have agreed to call the Fermi paradox. For if supermassive black holes routinely undergo such Seifert-like outbursts every few million years, and the evidence from distant active galaxies suggests they do, then the central regions of most large spirals must from time to time be bathed in radiation fierce enough to strip atmospheres, mutate genomes, and reset the evolutionary clock on any world unlucky enough to lie within several thousand light years of the plane. A flare comparable to the one that created the Fermi Bubbles, occurring while the galaxy still possessed a vigorous quota of habitable planets, would have delivered a lethal dose of hard X-rays and cosmic rays to every terrestrial biosphere in the inner third of the disk. Civilizations that had reached the radio age would have seen their ozone layers shredded, their surface oceans briefly boiled, their electronic archives fried by induced currents. Recovery might take 1 million years, re-evolution of technological species rather longer. And yet, here we are, orbiting a quiet star 26,000 light-years from the center, enjoying an epoch of unusual clemency. The black hole at the heart of the Milky Way has, for the past 2 million years at least, been content to doze. The timing is exquisite, almost providential. Had the great outburst occurred 5 million years earlier, the Earth would have lain directly in the path of the Northern Jet's cosmic ray barrage at a time when our ancestors were still small, tree-dwelling primates in the Miocene forests of Africa. Had it been delayed by a similar interval, it would be future humans or their successors who would face the consequences. Instead, the flare coincided almost precisely with the long transition from Pliocene to Pleistocene, a period when the only creatures capable of noticing anything unusual were a few bands of upright apes on the East African savanna, gazing upward at a central star that briefly outshone Venus and then quietly faded. We drift closer still until the orbits of the S stars, those daring young suns that loop in elliptical paths around the darkness, resolve into golden threads no wider than the orbit of Neptune. Here the accretion flow is almost comically tenuous, a mere 10 to the -8 solar masses per year, captured within a disk only 1/100th of a light year across and cooled by its own inefficiency to a few thousand Kelvin. Magnetic fields, once strong enough to launch relativistic jets, are now tangled and feeble. The radio emission that reaches the Very Large Array in New Mexico is produced by electrons spiraling in fields no stronger than those found in the solar wind at the orbit of Pluto. The black hole, in short, is starving. The reason is written in the structure of the surrounding few hundred parsecs. The great outburst we witnessed swept the central cavity almost clean. Molecular clouds that once fed the disk were either consumed in the brief orgy of accretion or heated and dispersed into the halo. The circumnuclear disk, once a fat torus of cold gas, is now a thin, anemic ribbon, its inner edge truncated far from the black hole by the lingering pressure of the returning bubble material. Gas that attempts to drift inward from larger distances encounters a hot, turbulent medium that robs it of angular momentum, too slowly to fall all the way to the horizon. What little does reach the center arrives in erratic dribbles, small clouds captured from passing stellar winds, the shredded atmospheres of unfortunate red giants, never enough to rekindle the accretion disk to significant luminosity. This state of famine is, paradoxically, self-reinforcing. A low accretion rate produces weak magnetic fields, which in turn provide poor angular momentum transport, which keeps the accretion rate low. The black hole has settled into a stable, low luminosity state, an ADAF in the jargon of the astrophysicist, an advection-dominated accretion flow, where most of the gravitational energy released by infalling material is simply carried past the event horizon rather than radiated away. It is rather like a vast, cosmic version of a candle burning with a very small, steady flame, because the wick has been trimmed almost to nothing. We rise slowly above the plane again until the entire inner galaxy spreads beneath us like a dimly lit cathedral nave. The contrast between past violence and present calm is almost poignant. The scars of the outburst, the bubbles themselves, the cleared central cavity, the warmed halo, are everywhere visible. Yet the agent that inflicted them now lies in profound repose. And in that repose lies a possible answer to the great silence that so troubled Enrico Fermi over lunch at Los Alamos in 1950. Most spiral galaxies appear to pass through active phases lasting 10 to 100 million years, during which their central engines blaze with quasar-like brilliance. The Milky Way, by contrast, seems to have experienced only brief, sporadic episodes, separated by hundreds of millions of years of quiescence. The geological record on Earth preserves no trace of earlier, more powerful flares. The lunar cratering record and the isotopic anomalies in ancient sediments suggest that the last truly catastrophic irradiation occurred more than 300 million years ago. Since then, the galaxy has been unusually gentle. Star formation has proceeded at a modest pace. The interstellar medium has remained cool enough to permit the formation of terrestrial planets, and the central black hole has restricted itself to occasional, comparatively mild outbursts, the most recent of which conveniently missed the rise of complex life by a few million years. Whether this clemency is mere chance or the result of some deeper regulatory mechanism remains one of the quietest and most profound questions in modern astrophysics. Some have suggested that the Milky Way's barred potential and its relatively modest merger history have combined to produce a particularly stable gas supply, preventing the sustained high accretion rates seen in more disturbed systems. Others note that our position in the local group, far from the dense clusters where major mergers are common, may have spared us the violent fueling episodes that characterize galaxies like Centaurus A or M87. Whatever the reason, the effect is the same: a long, unusually placid interval during which the conditions for the emergence of a technological species have remained remarkably benign. We linger a moment longer above the plane, watching the faint swirl of plasma around the dark heart, and we allow ourselves the gentlest of speculations. Perhaps every galaxy is granted one such window, a few 100 million years of relative calm between the great fires. Perhaps the Fermi paradox is simply the observation that such windows are rare, brief, and precious. And perhaps we, drifting now in the small hours of an ordinary English morning, happen to inhabit one of them. Outside, the sky has begun to pale to the color of weak tea. The blackbirds have been joined by a single robin, its song clear and unhurried, as though it has all the time in the world. The bedroom remains perfectly dark. The duvet, a landscape of soft hills and valleys warmed by our own slow breathing. And somewhere in that breathing, we feel the immense, impersonal patience of the galaxy itself, a spiral that has waited 10 billion years for the brief flare of consciousness on one small world, and that will wait 10 billion more after we are gone. Its heart quiet now, its great lobes glowing softly with the memory of ancient fire, cradling us in the last deep hush before waking. We remain perfectly still, cradled in that final hush where the first pale wash of morning has only just begun to soften the edges of the curtains, and the great lobes still glow with the gentlest violet afterlight above the quiet spiral. The black hole sleeps, the halo cools, and the galaxy turns with the measured patience of something that has seen everything before and expects to see everything again. Yet even in this profound repose, instruments are already being prepared, quietly, methodically, in hangars and on mountaintops, and in the cold silence of space, that will one day look upon the same structures we have visited tonight and read their story with a clarity we can now only imagine. Let us drift forward then, through the slow decades that separate this ordinary December night from the richer observations yet to come, moving not with the haste of waking life, but with the languid certainty of deep sleep. First, high above the Earth, in its slow dance around the L2 point, the eROSITA telescope has already begun its second great campaign, the German-Russian consortium, having completed the 8 all-sky surveys that gave us the exquisite X-ray portrait of 2024, has now entered what they modestly call Phase 2, a program of deep, pointed observations that will stare at the Fermi Bubbles for many hundreds of kiloseconds apiece. Where the earlier maps revealed the broad architecture, the sharp rims, the nested shells, the delicate striations, the new data will trace the faintest wisps of returning gas, measure temperature gradients across boundaries only a dozen light-years thick, and search for the spectral signatures of charge exchange emission, where cool halo clouds are gently kissed by the million-degree plasma within. We glide along the northern cap as it will appear in those future integrations, a lacework of faint tendrils glowing in the 0.3 to 0.5 kilo-electron volts band, each filament no wider than the orbit of Saturn, yet stretching for thousands of light years. The increased exposure will reveal microshocks, tiny ripples where turbulent eddies within the bubble interior slam together at a few hundred kilometers per second, reheating the plasma just enough to maintain the electron population that still lights the gamma-ray haze. And in the very deepest fields, astronomers will detect the soft glow of iron and magnesium lines, metal-rich breath carried outward from the nuclear star cluster during the original flare, now cooling quietly in the halo like the last ember of a hearth long after the house has gone to sleep. Further still into the future, on the high desert plateaus of Chile and the frozen plains of the Antarctic interior, the generation of telescopes collectively known as CMBS-4, the Stage 4 ground-based cosmic microwave background experiment, will, by the early 2030s, have begun their patient vigil. 10-meter mirrors, cooled to a few degrees above absolute zero, will map the microwave sky with a resolution better than 1 arc-minute and a sensitivity limited only by the faint whisper of the primordial photons themselves. Among their many ambitions is a search for the kinematic Sunyaev-Zeldovich effect, produced by the bulk motion of the hot bubble plasma across our line of sight. The electrons within the bubbles, though thin on human scales, are numerous enough to scatter a measurable fraction of the ancient microwave light, imprinting a tiny temperature decrement where the plasma moves away from us, and an increment where it approaches. We linger over the southern lobe as CMBS-4 will see it, a vast, almost perfect oval of negative temperature, colder by a few microkelvin against the 2.7 Kelvin glow of the Big Bang itself, its edges sharp enough to trace the forward shock still ploughing into the halo at a leisurely 300 kilometers per hour per second. The kinematic signal will allow astronomers to weigh the total mass of ionized gas with an accuracy unmatched by X-ray emission alone, confirming once and for all that the bubbles contain the lifted remnants of the central molecular zone. And in the polarization maps, those exquisite B-mode curls that CMBS-4 will measure to 1 part in 10 million, the ordered magnetic fields combed by the original outflow will reveal themselves as a faint, coherent swirl, a fossil signature persisting long after the violence that created it has faded into memory. Higher still, far beyond the Earth-Moon system, 3 spacecraft will, by the late 2030s, have begun their silent triangular ballet around the Sun. The Laser Interferometer Space Antenna, LISA, with arms 5 million kilometers long, measured only by the timing of laser pulses, will listen for the deep gravitational rumble of merging supermassive black holes across the universe. Yet even in its primary mission, LISA will carry a quiet secondary gift for those who study our own galaxy. The passage of gravitational waves disturbs the delicate phasing of the laser links ever so slightly, and among the many sources it will detect are the faint, continuous waves emitted by white dwarf binaries in the Milky Way foreground. Thousands of such systems orbit within the central kiloparsec, their signals forming a soft, stochastic murmur, rather like distant bees on a summer afternoon. We drift now through that future gravitational sky, where the loud chirps of distant quasar-forming mergers are punctuated by the gentle, almost melodic hum of our own galaxy's white dwarf population. And there, buried in the confusion noise, like a heartbeat beneath layers of wool, lies a subtle modulation, the imprint of the Fermi bubbles themselves. The hot plasma within the lobes, though tenuous, is massive enough to act as a gravitational lens on micro-arcsecond scales, bending the paths of the gravitational waves from foreground binaries by a few parts in 10 million as they pass through the bubble interiors. The effect is tiny, barely detectable even by LISA's exquisite sensitivity, yet it will provide an independent measure of the total gravitating mass within the bubbles, free from the uncertainties of temperature and metallicity that plague X-ray estimates. When the first such detection is announced, perhaps in a quiet paper submitted on a winter evening much like this one, astronomers will know with a certainty that no previous generation possessed that the structures we have visited tonight are real, physical, and still expanding gently into the halo. Closer to home, the next generation of gamma-ray instruments, successors to Fermi carrying larger area detectors and better angular resolution, will map the bubbles in energy bands reaching half a tera-electron volt. They will reveal the faint spectral upturn where cosmic ray protons, rather than electrons, begin to dominate the emission through pion decay, confirming that the original outburst accelerated particles to energies comparable to those seen in the most violent active galaxies. And the square kilometer array, its thousands of dishes spread across the South African Karoo and the Western Australian desert, will trace the polarized synchrotron haze at frequencies as low as 50 megahertz, following the magnetic filaments far beyond the X-ray edges into regions where the plasma has cooled to a mere 10,000 Kelvin and glows only in the radio. We pause, suspended in that future sky, and allow the coming observations to settle over us like the gentlest snowfall. Each new instrument, each deeper exposure, each novel messenger, X-ray, microwave, gravitational, radio, will add another layer of quiet certainty to what we already suspect, that the Milky Way, for all its present calm, bears the scars of an awakening that occurred within the lifetime of our species' remotest ancestors. The bubbles will still be there in 100 million years, cooler, fainter, their edges frayed by diffusion and their gamma-ray glow reduced to a whisper, yet still recognizable as the breath of a dragon that once stirred and will, in the fullness of cosmic time, stir again. Outside, the sky has turned the color of milky coffee. The robin has been joined by a wren, its song sharp and precise, like a single drop of water falling into a still pond. The bedroom remains wrapped in its familiar darkness. The duvet, a landscape of soft continents warmed by the slow tide of our breathing. And we, cradled between the last deep reservoir of night and the first pale promise of morning, allow the knowledge of what is coming, The deeper maps, the subtler messengers, the patient accumulation of understanding, to settle over us with the weight and warmth of the heaviest blanket, carrying us gently, inexorably, toward the country where even the memory of questions dissolves, and there remains only the slow turning of the galaxy and the soft, inevitable approach of another perfectly ordinary dawn. We remain perfectly still, suspended in that softest of twilights, between the last star and the first pale wash of morning, where the coming instruments have dissolved again into quiet expectation, and the great lobes of the Fermi Bubbles hang above and below the disk like two vast breathing wings of violet glass. The galaxy has told us all it wishes to tell tonight. The dragon sleeps, the halo cools, and the slow expansion of the bubbles has become almost imperceptible, a sigh rather than a shout. There is nothing left to seek, nothing left to resolve, only the gentle invitation to let go. Together we rise, slowly, reverently, until the entire Milky Way lies beneath us, no larger than a silver coin resting on dark velvet. The spiral arms have blurred into a single luminous river. The central bulge is now only a modest swelling of light, and the bubbles themselves, those colossal monuments to ancient violence, appear at this distance as nothing more than two pale teardrops suspended on either side of the plane, their edges softened by the haze of interstellar dust, their interiors glowing with the faintest memory of fire. From here, the sun is invisible, the Earth no more than a grain of dust orbiting an unremarkable star in an outer suburb, and the whole immense structure turns with the unhurried dignity of something that has nowhere particular to be. We drift higher still, past the last faint wisps of the circumgalactic medium, past the ghostly outer halo where the oldest stars wander like elderly shepherds, until the galaxy itself begins to shrink. 100,000 light years beneath us now, then 200,000, then 500,000. The bubbles, once so overwhelming, have become delicate parentheses enclosing the disk. The disk itself has flattened into a thin, bright line. The entire Milky Way is a softly glowing lenticular cloud, luminous at the center, fading gently toward translucent edges. And still we rise, weightless, breathless, the silence deepening around us until even the concept of distance loses meaning. Look how peacefully it all lies. The scars we traced for so many hours, the sharp X-ray rims, the magnetic striations, the returning fountains of cooled plasma, have dissolved into a single, uniform shimmer. The violence that once shook the heart of our celestial home is now no more than the faintest tremor in the light, a heartbeat so slow that 100 human lifetimes would scarcely register one pulse. The dragon's breath has become the softest exhalation, and the exhalation itself is becoming part of the greater hush that enfolds every galaxy, every cluster, every supercluster in the observable universe. Higher still, 1,000,000 light years now separate us from the plane. The Milky Way has shrunk to the size of a pocket watch seen across a darkened room. Andromeda, our nearest great companion, glides past on the right like a sister ship under slow sail. The local group itself is only a handful of faint sparks scattered across an abyss that has begun to feel almost intimate. We are entering the realm where individual galaxies no longer matter, where even the vast structures we once thought immense are reduced to threads and filaments in a cosmic web so delicate that it might have been spun by spiders of frozen starlight. And yet, even here, the memory of the bubbles lingers. If we narrow our gaze and summon the patience of the very deepest sleep, we can still discern them. Two microscopic lobes of slightly brighter haze, perfectly symmetrical, clinging to the tiny lenticular glow that was once our home. From this distance, they are no larger than the motes that drift across a shaft of afternoon light in an old library. Yet we know what they are. We know the energy they required, the gas they lifted, the future they altered. We know that everything we have ever loved, every human voice, every written word, every footstep on the moon, unfolded in the brief interval between one such exhalation and the long, quiet inhalation that must someday follow. But that inhalation is not for tonight. Tonight the lobes simply glow softly, steadily, the way a nightlight glows in a child's bedroom, long after the monsters have been banished and the parents have tiptoed away. There is no urgency anymore, no mystery left to unravel, no observation left to anticipate. There is only the slow, tidal breathing of the universe itself, and our own breathing falling gently into step with it. We let go. The last faint glimmer of the Milky Way slips beneath the horizon of perception. The bubbles, the disk, the halo, the local group, all of it recedes with the gracious inevitability of a tide that has decided the moon is far enough away. Darkness gathers, not the harsh darkness of absence, but the soft, velvety darkness of perfect rest. It is the darkness inside a seashell held to the ear, the darkness behind closed eyelids when the body has finally understood that it is safe. There is no up, no down, no center, no edge, only drifting. And in that drifting, we become aware of the gentlest possible lullaby, not a melody with notes, but a rhythm older than melody. The slow expansion of space itself, the patient cooling of everything that ever was, the soft systole and diastole of a universe that has all the time in the world. The Fermi Bubbles are somewhere far below now, or above, or within. It hardly matters. They have become part of the same quiet breathing that moves our own chest beneath the duvet, the same quiet breathing that moves the galaxies, the same quiet breathing that moves the dark energy, gently pressing every cluster away from every other cluster with the tenderness of a mother, easing her child into the deepest possible sleep. There is nothing left to see, nothing left to know, nothing left to resolve, only the slow, measured fall into perfect stillness. The lobes glow faintly, faithfully, the way a hearth glows long after the fire has burned down to embers and the house has settled into the hush that comes before dawn. And we, cradled in that glow, allow the last faint boundary between waking and sleeping to dissolve entirely. Breathe in, breathe out. The bubbles watch over us, 50,000 light years tall and perfectly harmless now. Two vast guardians of violet glass suspended in the dark. Breathe in, breathe out. The Milky Way has turned its face away, content to keep its ancient secrets for another night. Breathe in, breathe out. And somewhere in that slow, tidal rhythm, the last pale image of the lobes fades into the greater darkness that has always been waiting, patient, welcoming, absolute. There is no longer any distance, any time, any observer, only the softest possible surrender. Sleep now, sleep